Welcome to the workshop. For this workshop, you'll need the following: an OpenShift cluster at 4.12 or higher. Single node OpenShift with at least 32 gigs of RAM will work. A GPU node is optional, but it will significantly speed up the training. The cluster must have an internal registry configured with persistent storage for the workshop images. OpenShift pipelines operator must be installed. Dynamic storage provisioning must be configured. ODF for bare metal, LVM for snow, etc. And you'll also need access to a cluster admin account. You'll also need a workstation with a terminal. RHEL or CentOS or even OS X would do. You should have the Git client and Tecton clients installed. Optionally, you should have a still camera to capture images for input into your datasets. And finally, a webcam so that you can do live inferencing with the models that we're going to create in this lab. Okay, let's set up the workshop. We'll start by logging into our cluster from the workstation using the OpenShift console. Next, we'll clone the Git repo to our workstation. The link is in the description. Now we'll go to the Bootstrap directory under Flying Things and execute our first script. 01 create pipelines.sh, followed by whatever project name you want to use. For mine, I'm using modemo. If the project doesn't exist, it will be created. Let's take a quick look at what got created. In the console, navigate to Pipelines for our project. You'll see a number of pipelines. Let's look at Flying Things Images pipeline first. This pipeline builds all the necessary requirements for the workshop, including all images and supporting applications and services. A quick look at the parameters gives us an idea of all the configuration options. Next is the actual training pipeline. We'll go through it in depth shortly, but the main point is this pipeline can be used to create new custom models and improve them over future iterations. It has many adjustable parameters which can impact the overall precision of the model and available for adjustment and experimentation. Now let's go ahead and create our workshop environment. Do this by running 02 build image tkn.sh with the same project we used earlier. We see the pipeline is kicked off and we can monitor it from the console. This will take some time. Depending on your system, it could take anywhere between 13 and 30 minutes. So while we wait, let's talk about what's actually in the workshop. OpenShift is the foundation of everything we're using today. Its ability to securely run containerized workloads makes it ideal for our purposes. Since the nature of data science is experimentation and many iterations, its ability to consistently deploy and maintain multiple environments and configurations makes it a great foundation for ML operations. Tecton Pipelines is the engine that drives our operation. All the elements and tasks that make up our workflow have been automated and are managed by Tecton. As it's a Kubernetes native CI tool, it helps establish workflows that ensure consistent results with the flexibility to extend capabilities at any time. MinIO is an S3 compatible open source object storage service that we'll be using to store our artifacts. YOLO is written in Python, so the workshop is mostly coded in Python. For basic model serving, we'll be using FastAPI. It's lightweight and fairly simple to deploy with our model, and it has excellent Swagger interface which comes in handy for testing our model and even serving it to other applications and services. And finally, there's Label Studio. Label Studio is an annotation tool used to label datasets for input into AI/ML system training. We'll be using it to collect and label our image datasets. Checking back, we see that the bootstrapping process is completed in around 30 minutes. We see that all tasks have completed successfully and there are no errors. Let's take a look at what actually got created and deployed. In deployments, we'll see three apps: Label Studio, MinIO, and Model YOLO. Let's start with MinIO. We can use the root to connect to MinIO console. The username and password is minioadmin. We can see that there is a bucket already called Flying Things. In this bucket, the main thing to notice is a zip file called flyingthings-YOLO. This is the main artifact used in training our custom model. More on that in a bit. We'll come back to Label Studio later, but let's take a look at the model YOLO. As part of the workshop startup, we deployed a default YOLO model. This is useful as a baseline for what YOLO can do out of the box, and it's a good introduction to the Swagger interface. After clicking on its route, simply append /docs to the URL to access Swagger. All the endpoints are listed with some basic documentation and the ability to actually send and receive data. This comes in handy as you don't need to bother with a client that supports post requests when you need to do a simple testing. So let's do a quick test. Expand the detect function and click try it out to activate the panel. Now we can pick an image file to upload and have our model make a prediction. Let's pick something good. Perfect. Our model has predicted 20 donuts in our image. There's also an endpoint to show the image marked up with the bounding boxes and confidence scores, so let's try that one. And yes, we see 20 predictably delicious donuts. Our pipeline has the option to deploy the same model server for any custom model we create. This will come in handy for the workshop. So let's go over the workflow for creating custom models. Collect images. Ideally, gather many images of all objects we want to detect from different angles and lighting conditions. Annotate images. Annotation is the process of identifying objects in an image and drawing bounding boxes around them. Export artifacts. Once annotation is complete, we export the images, annotations, and classes in a format YOLO can use for training. This is stored in our object storage. Launch pipeline. We give our pipeline parameters like the name of our model, where the annotation export is, and what values to use during the training. Once the training is complete, the pipeline stores artifacts from the session as well as additional export formats so the model can be consumed by a host of other model servers. The artifacts are again stored in our object storage. Test model. Since our model was deployed with a fast API application, we can easily test it with the Swagger interface. Capture missed predictions. During the testing portion, it is important to test on images that were not part of the dataset. This will reveal any precision issues with the model. Missed or low confidence predictions can be collected and input back into the pipeline. Add images to dataset. We can collect all the missed images and add them to Label Studio where they will now be part of the dataset going forward. We then annotate as before and repeat the process until we have acceptable confidence levels in our predictions. Okay, let's put this into action for our first use case. We're going to make a custom model that can detect helicopters and airplanes. We'll then use that model on this drone footage I shot to identify this plane with bounding boxes. Here's the updated footage with the final model. For this model, I've downloaded hundreds of images of planes and helicopters from Kaggle and already created annotations for the set. You'll see it in flyingthings-yolo.zip file in the bucket. If we unzip the file, you'll find the class file and folders containing the images and labels. You can see the class file contains the two classes we care about, fixed wing and rotor aircraft. The images folder has over 300 pictures of all kinds of helicopters and planes. The labels folder contains all the labels for the images. In the file is the class ID and coordinates of the bounding boxes. Let's review what's in the pipeline. Fetch repo pulls our Git repo code into the pipeline workspace. Get dataset pulls our zip file into the workspace and unzips it. Create class file picks up the classes.txt file and converts it to a YAML file that can be consumed by YOLO. If the image size flag is set, the images will be resized to the maximum width. This module can be used in the future for other image preprocessing that help improve accuracy. Distribute dataset groups the files into three groups. 70% go to training, 30% go to test, and 30% go to validation. The groups are then moved to their respective directories for training. This grouping is done randomly in each run. If the GPU flag is set, the training requests go to a node with the GPU and runs the actual training on that node. If GPU is not set, the training is done with CPUs. Once the training is complete, the resulting model is exported to Onyx format for consumption by other model serving solutions. Now, all the artifacts from training including reports, model, class file, and exports are written to object storage where they are tagged and propagated to the appropriate folders. If the deploy flag is set, the Fast API app is deployed with the latest model. Finally, a summary of the pipeline run is presented with the parameter information. Alright, now it's time to run the pipeline and get our first custom model. Go to the same directory as before, flyingthings/bootstrap. Next, we'll edit the file 10-run-model-flyingthings-training.sh to change any parameters for this run. All the supplied parameters should be fine, but we'll want to change a few if we're not running a GPU. If your system has no available GPUs, then set GPU to N. Also, since there's no GPU, we'll need to change the batch size as it is set to maximize if there are GPUs. You should set it to 2 to avoid the memory issues. Now let's execute the script on the project we've been using. As the job kicks off, we can monitor it from the console. Here we see all the training tasks displayed for the pipeline. With GPUs, it should take around 5 or 6 minutes to run. CPUs will take significantly longer. We see this one took about 6 minutes, and all tasks slated to run completed successfully. In examining the logs, we see that the training task was able to fully utilize the GPU. We see that our model was deployed to model-flying things. Let's click on its route and launch the app. Let's send an image of a plane and see how well it inferences. Success. We have successfully identified something not in the original YOLO model. We then used that same model to identify the plane in the previous drone footage. Now let's review what we've done so far. We deployed a pipeline and supporting tools and images to OpenShift. We deployed pre-annotated images to object storage for input in the pipeline, instantiated the pipeline to build custom YOLO model where the pipeline ingested images, labels, and class files, pre-processed images by resizing them to maximum width, distributed images to train, test, and valid groups for YOLO training, trained a custom YOLO model, exported our custom model to Onyx format, saved our model export and training artifacts to object storage, deployed our custom model to OpenShift in a containerized fast API application, and validated our custom model by interacting with API endpoints. Stay tuned for the next chapter where we create custom models from our own custom images.